All right, these are questions 1 through 24 for chapter 29, and this is the last part of chapter 29. The first part of chapter 29 was about light and mirrors, and this part is about the bending of light, and we call the bending of light refraction. Refraction is basically just caused by different speeds of a wave, and you can do this with water, you can do this with light, you can do this with anything that forms a wave. So the refraction itself is we're just speeding up or slowing down the wave. It occurs whenever a wave changes speed. So questions 1 and 2 are basically the same. And this is kind of a neat phenomenon. You'll see that this pencil is actually all the way down in the bottom of the cup. It doesn't look like it here. It's because the light is bent so well that you really can't see the pencil down in the bottom of the cup at all. You just see it up in the top. And you actually see the pencil looks bent here and actually broken over on this side, broken over here too. Kind of a fun little effect. For number 3, light refracts or bends through a lens or through air that is very, very thick or very, very thin. And because sound is also a wave, it can refract just like light since both have a wave nature. So if I have myself and I am yelling at my wife, she's on the other side of the lake, and the lake is very, very cool on the surface, and the air above it is cooled by the lake. And the warm air up top is just coming in from the atmosphere. When I start yelling, that actually will bend or refract and come back down, and she'll hear me really well. So on a nice warm day, if the lake has been really cool, you get a slower speed of sound here and a faster speed of sound up top, and that actually bends or refracts the sound waves. So same type of thing. Number 4, if I look at a penny that's been dropped inside a cup, you'll notice this penny looks really big. It's even distorted a little bit. But if you drop a penny inside a cup, it'll actually magnify that penny a little bit. And it's because the light waves are going through the water pretty slowly, and then when they hit the edge of the cup, they actually speed up, and then we see that. For number 5, anytime I have a beam of light, let's say that I have a laser and that laser is in water. So this is a line here, and we actually would have the laser pointing down to the right. When it hits the air, so we might have, I don't know, kind of this type of thing where you've got a laser shining light down into the water. It gets bent toward the normal when it goes from an index of refraction, so we know that the index of refraction for air is about 1, to a bigger index, and water is probably about 1.3. So you'll see that it bends toward the normal. It makes this angle smaller. This angle is big, and then it bends toward the normal. When the light comes off the mirror, notice that when it goes from the water into the air, we have a really big angle here compared to what we have for this one down on the bottom. So the answer to number 5 is away from the normal. Whenever you have water and you have light traveling in the water and then it comes out of the water, it actually is going slower in the water and it speeds up when it gets out of the water, back up to the speed of light in air, which is about 3 times 10 to the 8th meters per second. For number 7, if you look at somebody in the water, their legs will appear shorter due to that refraction effect. So you can notice that this lady's thigh looks really, really short. It looks kind of funny just kind of looking at it this way. For number 8, the mug will actually, if you, let's say you put root beer in a mug and you fill it, the mug will actually appear fuller than what it really is, and that's because of refraction. You'll notice this cup is the same way. Notice that this height is the actual height of the water, but if we look at it from the outside, you actually see it looks like it's a little bit less, a little bit more full than what it is on that side. Kind of a cool effect. Number 9, light travels the fastest in a vacuum. And air is very, very close to a vacuum, so it's about 99% of the speed that light would have in air, in a vacuum. In water, it's about 75%. If you look at, this would be titanium white, it would travel pretty slowly. It's about 40-some%. They've done some experiments now where they've slowed it down so much that you can actually see the photons or the bundles of light traveling through. Number 10, stars twinkle on Earth due to the atmosphere. The atmosphere actually will bend the light, and it looks like the stars are twinkling. If you were to go to the moon, though, and look up, you would not see the stars twinkle because there's no atmosphere on the moon. Number 11, for this one, they're talking about light going through, and part of it is blocked off. And your final answer here is 81%. So if you're using similar to polarizing filters, if 90% of the light comes through the first time, and then you do 90% of the 90% the second time, you actually get 81%. That one's kind of tricky. Number 12, a mirage is mainly due to refraction. So the light comes down, it hits the surface here. The air above the surface is warmer than it is up up away from the road, and so it actually bends the light. You see this reflection, and it's due to the refraction of the light. Number 13, in order to see a mirage, typically it's on a hot day. You have a layer of hot air just above the road, and you have cooler air just above that hot air. And because of that, you get bending of light, and you actually get the reflection due to refraction. And we call that a mirage. Number 14, a wet spot mirage. What are you seeing when you see the reflection? You're actually seeing the sky. You'll notice that the car here is white. You'll see some of the telephone poles being reflected off of the pavement. And then the blue here is actually the sky. You can see some of the reflections here, like the grass. You see the car tire, the pole, but on this one you can really see the sky really well. For number 15, the following things are the consequence of the refraction of light. Rainbows, mirages, and then we'll talk a little bit about this. This is called total internal reflection, where if you're underwater, when you look up at an angle, it looks like a mirror, and so it looks like you're looking into a mirror. If you look straight up, you don't. For number 16, they wanted to know what color light would travel the fastest as it goes through a prism. And that's going to be red, because red has the longest wavelength, the lowest frequency, so it's bent the least. Violet will actually travel the slowest. It has the highest energy, and it is bent the most, so it's really easy to get it to go. Number 17, if I refract sunlight, you'll notice that I get all the colors of the rainbow: red, orange, yellow, green, blue, indigo, and violet. So that one's pretty simple. The average speed of the light does just depend on the color of the light. So some of these are going to travel a little bit faster than others. In a vacuum, different colors of light travel at the same speed. They only have a different speed in a transparent medium, like air, or in this one, this is a glass prism. So we can slow them down going through the prism. So the violet's really slowed down and has a slow speed as it's traveling in the prism. But as they get out, all these colors outside of this prism are actually traveling at 3 times 10 to the 8th meters per second. Inside the prism, this one, red, is closest to 3 times 10 to the 8th, and the violet would be the furthest away. So that's why this one's a little bit confusing. In a vacuum, outside of a prism, different colors of light travel at the same speed. But if you have them like in air, or this would be kind of water vapor mixed with air, they travel at a different speed. For number 19 and number 20, the outermost color and the outermost bow of a double rainbow is blue. So notice that here's the primary rainbow, here's the secondary rainbow, and the outermost color there is actually blue. The second rainbow is dimmer because there's an extra reflection inside the water drops. So there's water drops around here, and the extra reflection actually produces the second rainbow that you'll see. For number 21, if you're flying in an airplane and the light is traveling around the airplane, you actually see the airplane inside of the rainbow if there's a rainbow formed. And it's because all rainbows are actually circular, but the Earth gets in the way, and so we only see the rainbow that you see here. For number 22, rainbows use a couple of things. They use refraction, so the light is bent, but they're also what we call totally internally reflected, and we'll talk a little bit about that later. But you'll notice that they go in, they're bent when they go in, and then that light bounces, and when it bounces, we call that internal reflection. So rainbows actually use both of those in order for you to see them. And like we said, the Earth gets in the way, otherwise those rainbows would be circular in nature. Optical fibers use this total internal reflection also. So when we take a beam of light, monochromatic means it's one color. When we have it hit the inside of the optic fiber, it actually will bounce back and forth. And this is how we communicate now. When you make a cell phone call, it goes to the cell tower, then down the tower into fiber optic cable. And that travels very, very quickly from one place to the other. This little diagram on the bottom also shows most of the light here, when you're not at a very big angle, goes right out of the fiber. But once you get to the point of letter E, all that light now is bounced back. So we call that total internal reflection. And then 24. This one is total internal reflection. This should kind of shows you what it does. If I look at this turtle from a distance, I see that the water, the bottom surface of the water, actually makes a mirror. It's because all the light is reflected off of the bottom surface. Same thing's happening here. It's hitting the prism at a pretty big angle from the normal. And when it does that, it actually bounces off and you don't see light go through. So it acts a lot like a mirror. It's very, very weird how that happens. If I was to be in this probably looks like a lagoon, or maybe we're out in the ocean. If I was to look straight up, I would actually be able to see the sky and things. That's why people fish just off a shore. And those are 1 through 24.